right, here we are. Welcome to our first ever Zoom session. So first, let me turn on the screen sharing. Let's see, where are we? Oh, I am doing it. Okay. So what are we doing today? So we have finished with our second midterm, of course. That means we're done with chapters 12 and 13. And now we're ready for the last chapter of the semester, which is 15. Only 15. But when you see it, you'll say, I can see why the entire final can be based on chapter 15. It's kind of involved. And in the beginning, there's going to be a lot of background that we have to go through, and it's going to seem very abstract and maybe even scary. But as always, we'll get used to it very quickly. And once we start using the calculators, we'll be able to get our results very quickly and easily. And also, I'm going to use some Excel this time just to show you how regression analysis works and how you can implement it on Excel, although that will not be part of the final exam. So anyway, in the meantime, let's introduce this topic. We have simple regression analysis in chapter 15. And so what we're actually trying to do here, in a nutshell, is estimate the relationship, the equation of a straight line. What does that mean? Well, we're going to assume that there's two variables that we're trying to analyze, and we assume that they're related to each other in some important way. Typically, one of them will be a dependent variable, which is y, and the other will be an independent variable, which is x. And what we're trying to accomplish here is to estimate not just the direction of the relationship between the variables, but the strength. Okay, so just as a quick, simple example of this, imagine yourself working in a corporation's marketing department. And it's important to know if we're wasting our money on advertising or not. Okay, so, companies obviously do a lot of advertising. The question is it worth the money? And you're working in a corporation that's trying to decide every time we spend $1 in advertising, how much extra revenue is that bringing us back? And is it a good investment? So we can do that with regression analysis. And what we're going to wind up with is an equation for a straight line, which presumably tells us how much each extra dollar in advertising is contributing to our bottom line. Now, once that's done, we can also use the results to do forecasting, where we can say, for example, suppose that next year we're planning on spending $100 million in advertising. That being the case, how much should this contribute to our profits next year? So it's a very valuable tool to have, very useful for a lot of applications. In fact, you'll find that if you do any research in the future in any of your classes or on the job, chances are regression analysis will be an important part of that. Now, it's a very complex topic, but luckily for us, we can use our calculators to get the results that we need. And we'll go through that probably the next time we meet, not today so much. Yes, our calculators, as usual, will come in handy here. But also, like I was saying before, we could use Excel, and we'll do that not today, but maybe next time. And also, a lot of specialized software packages are out there which can be used to actually generate the results for us. But there's a lot of information here that we need to understand how to interpret it. So ultimately, our goal is not so much to generate these results, but to interpret them. Now, there's two basic types of regression analysis. We're only going to do the first one in this class, the simple regression, but there's also another type of regression called multiple regression, which you may run into at some point. And I'll briefly explain to you what it means, but we will not have time to do that here. Part of the reason is because it's much more complicated, and also because the calculators are unable to do multiple regression. With that, we've kind of reached the limits of their abilities. So we'll focus our attention here on just the simple regression. And even that's fairly complicated. So how does this work? Well, as I started to say earlier, we're going to assume that there is a relationship between two variables such that one of them depends on the other. Okay, so as you know, from using the XY coordinate system, when we have two variables that are related to each other, one of them typically depends on the other. And so we illustrate that in the following way. Oh, I don't know. Let's say we have the relationship y equals 3 plus 4x. Okay, so you can see that whatever y is, y depends on x. So we say that y is the dependent variable. X is the independent variable. Now, the actual equation that we have here tells me two things. Number one, the intercept is 3. Or think of it this way. This is the point 0, 3. Okay. At this point, x is 0, y is 3. The slope is 4, which means that sometimes it's drawn like this. The slope of 4 means that when x increases by 1, hold on. Y increases by 4, but it also goes in both directions. In other words, if x rather decreases by 1, x will also decrease by 4. So we'll say vice versa. And this is what it means to have a slope of 4. All right, so once again, the slope of 4 means that any 1 unit increase in x or decrease leads to a 4 unit increase or decrease by y. And then the intercept simply tells me where the line cuts through the vertical axis. Or you can also think of this as the idea that y equals 3 when x equals 0. So with regression analysis, what we're trying to do is estimate the equation of this straight line based on the assumption that the relationship between the variables is linear. Now, that's a big deal, by the way. If not, then what we're doing here is not going to give us very good results. So in order for this to work, we have to first assume or make sure that the data we have has at least a reasonably linear relationship. And one way we can figure that out is use a special type of graph which you'll see in a second. I'm sure you've seen this before. In order to determine if the relationship between two variables is linear, you can use a scatter plot. Yes, the scatter plot. Yes, I'm sure you recognize that from your travels. And how does that work? All right, let's take a look. All right. I think I can minimize this. It's wasting a lot of my real estate. Let's see. By the way, oh, I forgot to mention up front. I see you've already all your microphones are muted. That's good. That way there's no background noise. But also, if you do want to ask a question, you can just unmute the microphone and then just ask. Or else, if you want to, you can just type something in the chat box. That also works. Okay. So actually, in the meantime, I'm going to move this somewhere else. There we go. It's just wasting all my space. Okay, now, what does a scatter plot look like? Well, basically, it's a group of dots. I mean, that's all it is. But they mean something very important. So, for example, suppose we are considering that case with sales and advertising dollars. Based on the assumption that sales depend on advertising. So what you're typically going to do is you're going to gather up data. And let's say that you go out and obtain data for your sales and your advertising for the last, let's say, 20 years. The way this works is that each point in this plot represents a single year's sales in advertising. So this point I'm showing you here now, for example, might be 2020 sales in advertising. It's understood that the y coordinate is the sales and the x coordinate is the advertising. And then this could be, for example, the year 2021, and this could be 2019, and so on and so on. And so what we're really after here is the pattern, if there is one. We're hoping to see if these data follow more or less a straight line. Now, clearly, the relationship looks linear, although it's not perfect. It's never going to be perfect. You can see, though, the points are pretty close to this line, which is itself has a positive slope. So what this plot is telling me is a couple of things. Number one, the data are approximately linear. And number two, there's a positive relationship between X and Y, meaning that they're moving in the same direction. How can you tell? Because the slope of this line, which is often, by the way, called the trend line. Sometimes it's called direct. X and Y have a positive or direct relationship, which simply means that as advertising goes up, sales tend to go up as well. That's all we know just yet. Okay. There's a tendency for them both to go up at the same time. Although you'll notice that because they're not all straight on that line, there's some deviations there. The amount by which advertising goes up and sales goes up is not always the same. Okay, so this is something that we don't see in other disciplines. Like, for example, somewhere in here, I've got a little graph that shows the relationship between Celsius and Fahrenheit. Now, that's a very different ballgame. This is a very precise mathematical relationship. There's no exceptions. When the Celsius temperature goes up by 1 degree, the Fahrenheit temperature goes up by 9/5 of a degree. So that's why it's a straight line, a perfectly straight line. You don't see points scattered all over the place. And so because of that, this is referred to as a deterministic relationship. All right. A deterministic relationship means it's an exact relationship like this one. No exceptions. Okay, it's a straight line. The one we're seeing here with our sales and our advertising, because there can be some deviations in there, this is sometimes referred to as it's called a probabilistic relationship. Meaning that it's not perfect like the deterministic relationship. Now, that will cause complications, of course, but we will try to account for them with our regression analysis, the fact that these points are not all right on the line. But what we're trying to capture is the general, the core relationship between X and Y. All right, so now the big question becomes, how do we do this? Okay, and of course the calculators, I'll show you later on how to do this with your calculators and Excel, but we want to understand what's going on behind the scenes first, and this is where all the complexity comes from. The names of all these new concepts can get a little scary at times, but that's all right. We'll get used to it very quickly. So remember, with simple regression analysis, which is what we're seeing here, we're focusing on the relationship between a single dependent and independent variable. Multiple regression, which we'll not be covering, means that we're allowing for the possibility that there could be two or more independent variables. Okay, so let's say that instead of sales depending on advertising only, let's say that we assume that sales depend on both advertising and the prices that we're charging. Then that would require us to analyze that relationship with multiple regression analysis, because these are both independent variables. Okay, so in other words, we'd have y would be our sales, and then we have two independent variables. We'll call them x1 is advertising, x2 is prices. Okay. Now, if you're with Excel, it would be a breeze to do this. But sadly, our calculators don't have that functionality, and so we're not going to do it anyway. But if we did want to run multiple regressions, we would need to go to Excel. All right. Now here, this is just another illustration of what the relationship between x and y. We normally assume that y is the function of x, and x again is the independent variable, y is the dependent variable. This graph, though, you see this is just a curve. It is not necessarily linear. With simple regression analysis, we are assuming linearity, which, by the way, if it is not, if our relationship is not linear, we have to do one of two things. We either have to try a different approach, or else we can make modifications to the data, but we will not do either of those here. So just, it's not the case that you can never use regression with nonlinear data, but there's a lot of extra steps involved. Okay, now we're going to switch our attention to this example, the relationship between height and weight. And I think you'll all agree that people's weight depends on their height. It's not the other way around. And therefore, we'll define weight as the y or dependent variable, and height will be our x or independent variable. So what we're going to do here is, of course, draw a scatter plot. And you can see, and by the way, in this case, we only have positive values. We can't have negative weights or heights. So all of our data are found in the first quadrant. And again, we have a trend line with a positive slope, which tells us that as height increases, there's a strong tendency for weight to increase, and vice versa, which implies a strong positive or direct relationship. What we don't know just yet is how much weight goes up when our height goes up. Okay, that's what the regression analysis will tell us, the exact details. I want to know, for example, if a person is 1 inch taller, that would add 10 pounds to their weight or something like that. All right, right now this is fine as far as it goes, but we don't have the exact numbers yet. Now, here's a fun example from finance, which you'll be seeing a lot of in the spring. We're going to be looking at the returns to stocks. Now, before we do that, in case you've never heard of it before, the Standard & Poor's 500, which is often abbreviated the S&P 500, is a stock market index. Basically, it is an average of the 500 largest stocks in the United States. It's an important index because it is a good indication of what's happening in the overall economy. When the S&P goes up, that means things are going well. When the S&P is going down, things are not going so well. And in fact, if you look at any website that's dedicated to investments analysis, you'll see that one of the first things they will want you to know is what's going on with the S&P 500. Well, the red means not good, but if you notice right now, it's selling for $45.33.90. It's down $13. That's not such a big deal. The Dow is down a little bit. The NASDAQ is down a little. It means the market's having a slow day, which is not unusual just before a holiday. You can't really read anything into that. This is probably what's going on. Home sales fell to a 13-year low in October as prices rose. That's bad news, no matter what's going on with the holidays. But anyway, so that's the S&P 500, and everyone watches it very closely in the markets, and you'll be discussing this in your first finance class next spring. But what we want to do here is see if there's any connection between the returns of that Standard & Poor's 500 and Apple stock. So Now, by the way, Apple is part of the S&P 500, so we know there's a connection there. But what we're really interested in knowing is this. If the market is doing well, meaning the S&P is going up, what impact does that have on the returns to Apple, and vice versa? For example, if the S&P 500 goes up 1%, what does that do to the returns to Apple? Does it go up 1% or 2% or whatever? That's what we're trying to find out. How strong is this connection? So we're going to assume that the returns to Apple depend on the returns of the S&P 500 because the S&P 500 represents basically the overall economy. And so it stands to reason that the returns to Apple will depend on that. So you obviously gather your data. And by the way, since these are returns, we can have negative returns. Now the points are scattered throughout all the quadrants, not just the first. Okay, so that's because we can have negative returns for both. And so you can see there's a strong positive relationship. Of course there is. The question is, what are the slope and the intercept? That we'll find out when we start running our regression analysis. All right, so now I think we understand what this is all about. And like I said, multiple regression would mean that there's two or more independent variables. Let's take a look at a quick example of this. This is straight from economics. What if we're trying to study the relationship between the yield on a 90-day treasury bill? Now let's take a step back here. Everybody knows that the U.S. government racks up massive deficits every year, and they have to pay for them. They have to pay for the things that they buy, just like everyone else. If they don't bring in enough taxes, they borrow the difference. And how do they do that? They issue treasury bills to the public. When you buy a treasury bill, you're lending money to the government to pay its bills. And in exchange for that, you get some form of rate of interest to compensate you for lending them your money. Those numbers are watched very closely in the market every single day. But this economist wants to see what is the connection between the treasury bill yield and two independent variables, the growth rate of money, the money supply, and the growth rate of the real GDP or the overall economy. So that means that you've got one dependent variable, of course. There's never going to be two dependent variables. That would be here. But now all of a sudden we have two independent variables. The growth rate of the money supply is X1, and the growth rate of the real GDP, we'll call it X2. So that means what we're analyzing is the relationship Y equals F of X1 and X2. And that requires us the use of multiple regression. We're estimating the relationship between three variables. Interestingly enough, we can no longer draw this as a straight line. This now requires us to draw it as a plane, which is very complicated. I find it very difficult to draw this properly. Something like that. But yes, so it gets very involved very quickly. All right, so now we're going to remind ourselves exactly what a linear relationship is. Obviously, this is a relationship that can be described with a straight line. And of course, everybody in the planet remembers that the formal equation for straight line is y equals mx plus b. Actually, this is not the only way to write out a linear equation, but it's the most useful, in my opinion. Y equals mx plus b. And so let's remind ourselves what all these terms mean. M is the slope. B is the intercept, or the vertical intercept. So there's a graph on the next page that'll help us visualize this a little bit better. What's happening here is that here's our straight line. The intercept is B. This is the point 0, comma B. And M is the interesting one. In regression analysis, we rarely are interested in the intercept. It's the slope that we're really looking for. And so if you remember formally, the slope is the change in y divided by the change in x. You can see that sometimes written as delta y over delta x. Okay, that's a more formal expression. Oh, it's all coming back, isn't it? Yes, it is. You may also remember it being called in high school the rise over the run. To help remind you visually what that looks like. In other words, the rise is the vertical direction, the run is the horizontal direction. But ultimately, what it means is if x changes by 1 unit, what happens to y? And usually, in most studies, that's the number that we're interested in. So let's go back and revisit our example about the sales and advertising. Where is it? All right, let's find that and do that later. Here, the slope would tell me how much weight, how much, let's put it this way. It would mean for each extra inch of height, how much heavier should a person be? That's what it would mean here. With the Apple and Standard & Poor's data, that would tell me if the S&P goes up 1%, what will be the impact on the Apple stock? Okay, so it's a sensitivity of y to changes in x. That's what we're capturing. So I will add that little discussion here. So ultimately, the slope represents the sensitivity of y to changes in x. That's ultimately what we're after. Okay. Although it's usually measured with the assumption that x changes by 1 unit. So if x is in dollars, for example, we want to know what a $1 change in x does to the value of y. All right, so a lot of this is stuff you've seen before, which is good. And of course, the intercept, like I said, often we don't really need to worry about it. It's the slope that we're interested in. By the way, I've done some scatter plots in Excel. I want you to see a couple of key results. Here's a case where the two variables are almost perfectly linearly related to each other. Look at that. It's almost a perfect straight line. You don't see that very often in practice, but it's pretty clear here that x and y have a linear relationship with each other. And that's exactly what we're hoping for. Now let's look at a case where that's not true. Look at this one. Oh, now you can see that at first x and y seem to be linearly related, but then as we get further and further up here, all of a sudden it's not linear anymore, is it? The thing is here, that trend line, which is called an exponential trend, the slope is getting steeper. And that's something you do not see with a linear relationship. So the slope rather is getting steeper. As x increases. That means it is not linear. So if this is the data that we have, we should not use the traditional simple linear regression model, because if we do, the results will not be very useful. Now, that doesn't mean there aren't ways we can get around that, but we will not be doing that here. Okay, it does complicate things quite a bit. So if we see this on our scatter plot, we stop immediately and say, maybe we should try something different. Okay, because regression is based on the assumption of a linear relationship. All right. So that's why we like the scatter plot. It's a quick and easy way to make sure our assumptions are correct. If not, then we know in advance before we waste a lot of time doing a linear regression model. All right, now here we go. Now this is where it's going to start to get a little bit scarier. I just want to remind everyone that starting from way, way back in the beginning of Stats 1, we were introduced to the idea that we use samples instead of population for the most part, because samples are easier to obtain and less time consuming. So for example, we use X bar. Just throw this in here again, a quick reminder. You rarely have access to all the data in a population. Instead, use samples to estimate the properties of the population. For example, sample mean X bar is used as an estimate of the population mean. By the way, if you've ever wondered about this, suppose you need Greek letters in your document. You go to Insert, Symbols, and voila. All right. Well, okay. Now, why did I even mention that? Because this is what we're about to do. With regression analysis, we assume that there is a population regression line which best fits the data found in the entire population. Actually, I'm going to put another word in here too. Fits or explains the data found in the population. We usually do not have enough information to estimate the entire population line. So what do we do about it? Instead, we use samples to estimate a sample regression. So when you type numbers into your calculator, what's going to pop out of it are the slope and the intercept of a sample regression line. Now, having said that, what we're going to do is look at the equations for both, though. Okay, so we need to understand properties of, or I guess what I should say is the notation used for the population regression line and the sample regression line. And note the differences. Okay, so here we go. So we're going to start by introducing the population regression line. And if you recall, by convention, we'll use Greek letters here because it's a population measure. And so here we go. Now, there's a lot of writing on here, but right here, this is our population regression line. And you can see we've got some new Greek letters in here. We have the one that looks like a B is beta. One that looks like an E is epsilon. So there's a lot of strange things going on here. You can see it does kind of resemble a straight line, doesn't it? The beta 0 is the intercept. Beta 1 is the slope. But then all of a sudden, there's some new things here that we don't normally see in a straight line, like up here. For one thing, what is that epsilon doing there? What is that supposed to be? Well, this is known as an error term. And we'll discuss that in a second. Secondly, you notice there are subscripts. What? Okay, well, what is that all about? Well, each element of our sample, population, can be identified by this index. So in other words, Every element in our population is identified by an index, so that, for example, X1Y1 might represent sales and advertising in year 2020. X2Y2 might be the same thing for year 2021. So we need to keep track of each one of these. We need to know which point is which, and that's why we do this. Now you'll see why this is important in a second. So we've got the index, which is something new, and we have the error term. Now, all of this is made necessary by the fact that our data is not all right on the regression line. Otherwise, we'd have the same situation we did with Fahrenheit and Celsius. There's no error term, there's no indexes, it's just a straight ahead function. So on the next graph, next slide, I've got some, I've got a little graph here for you to look at. So this is our regression line for the population. So the key here is that for each point, let's say X1, Y1, you notice how that value is above the regression line, which means that the regression equation is not perfectly accurate. For that point, you notice there's a vertical distance between the actual point right here and the estimated point on the regression line. That vertical distance is known as an error term. Okay. Specifically, because it refers to this point, X1, Y1, the error term is listed as E1, one meaning the first element in our data set. The value of this error term is always going to be calculated as actual Y minus estimated Y. So it represents the fact that the regression equation incorrectly predicted where Y should be for that particular X. And if you notice, the same thing is up here. I've got an E2 here for this point. So also, if you notice, epsilon 1 is positive, epsilon 2 is negative. And they're not equal to each other. So in other words, every point is unique. It has its own unique distance to the line. And that distance is the error associated with that ordered pair. So almost every one of these points, now there might be a point or two that are actually on the line, like this one, for example, has no error. The error is 0. But most of them have an error. It's either positive or negative. So those epsilons are there to capture that effect. How far off is the point from the line? Now, this is something we've never had to deal with before. That's what makes it so complicated, these error terms. If only we had data that was perfectly linear, but we don't. Now, why is this happening, by the way? Why can't we have a perfect relationship? Well, there's a few potential reasons for this. For one thing, whatever Y is, there's a very real chance that its value is dependent on not just X, but other variables as well that are not included in our equation. So let's say with the advertising and sales, sales may depend on variables other than advertising. And that's why those points are not perfectly on the line, because we're missing something. Also, the data itself may have errors in it. Whenever somebody gathered this data, maybe there's actual mistakes. And some of the assumptions of regression analysis may not be true. In other words, for example, relationship between sales and advertising is not um, perfectly linear. That would be a violation of the assumption that the two variables have a linear relationship, and that would also cause there to be error terms. So it's very frustrating for us, but that's just reality. Now, I've also got a graph showing the same type of thing for weights and heights, so you can see again how errors arise and what they look like. Okay, so let me quickly show you that. Actually, let me give you a second to catch up. This is one of the unfortunate things about being online. I can't see what you're doing. I can't tell if you're caught up or not. In the classroom, it's very obvious and people still need more time. Not so much here, so I'll give you a minute to catch up with this. All right, so let's look at this graph. It's very similar to the one we just did. Oh, I don't know if I mentioned this or not, but this document, which is called Chapter 15.8 with notes from 11/21/23. I'm going to be posting this on the Blackboard along with the video or the recording. The recording, if it fits on Blackboard, I'll put it there. Otherwise, I'll put it in my YouTube account. This one I'll be putting on Blackboard, so you have the original notes, but also you have the ones that I've just created today, the ones that I wrote. So you won't lose any of this. All right, so here again, you can see I'm trying to focus on the errors. I've chosen error 4 and 3. And you can see error 4 happens because the y, this point is well above the line. We'll call that epsilon 4. Let me neaten that up because it refers to the point x4, y4. And you can see epsilon 4, because of the way the error is defined, is positive. Okay, so if the point is above the line, the error is positive. Whereas with error 3 up here in the right-hand corner, it's the other way around. The point is too low to be on the regression line. So therefore, this is negative. Okay, because the error itself, remember, equals actual y minus estimated y, where the estimate is the point, the location on the regression line. Now, by the way, we'll see in a few minutes that one of the assumptions of regression analysis is that while we have all these error terms, they should cancel each other out. In other words, they should add up to 0. So in other words, sometimes the points are too high and sometimes they're too low, but on average, they should add up to 0. If they don't, then something's not right. That means you have to check your results and see if there's a problem. Let me just show you a couple of new graphs that would illustrate something like this. I'll just mention this now. One of the assumptions of regression analysis is that the error terms should add up to 0. In other words, positive errors will cancel out the negative errors. It's just like, let me give you an analogy for this. I like analogies. Suppose you have a scale at home, and sometimes it overstates your weight, and sometimes it understates. As long as these errors offset each other, or in other words, on average, weight is correct, then you can use the scale, knowing that it is reasonably accurate. On the other hand, if the scale always overstates the weight or always understates your weight, it must be adjusted. You know what I mean? It's like, what is that good does it do, knowing that it's always 10 pounds off? And so the same thing is here with the regression analysis. The errors, we're fine with the errors as long as they average out to zero. So let's see what it would mean if they don't. Let's say, here's our points. I think I can copy and paste these. Oh, maybe not. Oh, there we go. Oh, that's kind of helpful. So what I wanted you to see is here, this is what we're aiming for. Average epsilon is zero. What about this one? Ooh, that's not a good one, because here you see the line is too high, and here the line is too low. And since remember the error is the actual minus actual y minus estimated y. It sounds backwards, but here the average epsilon is negative, and here the average is positive. So these two violate the assumptions, and that means we have to change something. That's not acceptable. We have to have a case where the error terms offset each other. Otherwise, the results will be pretty much useless. All right. Now the indexes, I think we already understand the indexes because they refer to specific elements in our population. All right. So by the way, I just want to show you these points that we're estimating. Now this is where it gets really messy, are actually centers of probability distributions. And those distributions are normal. So in other words, the line itself represents the centers of these distributions. If all the points were truly on that line, they'd be at the centers of these distributions and we'd have no errors. But in reality, the points can be anywhere, although the probability of getting up way up here and down here is very low. And so what we're actually doing is creating probability distributions with these error terms. Ideally, they'd all be in the center, but in reality, they can be scattered across the line. But we can calculate their probabilities using the normal distribution. And if you notice in the bottom, it specifically tells us that each curve has the same standard deviation. That's an important assumption of regression analysis. All right. So now we're going to quickly look at the assumptions of regression analysis, which we briefly discussed. The first thing is the epsilons are normal. The mean is 0, meaning that the line is at the center of these normal curves. Also assuming that the standard deviations are the same. Okay. The standard deviation is important because here's what effect it has on our results. In the graph on the left, you notice how the points are all very close to the line. That means we have very low error terms. The standard deviation is also very low. The one on the right, the points are pretty far apart. The standard deviation is very high. So this is what the standard deviation does to our results. Low standard deviation, the points are close to the line. High standard deviation, they're far from the line on average. So that means that in the left graph, we can have a very high level of confidence in our results. The one on the right, we cannot. That's what we don't want to see. All right. Now, here's another good graph to show you the same idea. In the one on the left, the standard deviations are the same, more or less. The one on the right, they're all different. Okay, so this one violates the assumptions. This one matches the assumptions. Meets the assumptions. Yes. So the one on the right, if you saw that happening, you'd have to do something different with your regression results. Now, the third assumption here is that the error terms are not affected by each other. In other words, they're independent of each other. What does that mean? They're independent of each other. Well, in a nutshell, it means that there's no pattern to them. I'll show you a couple of graphs that illustrate this. So on the left, they're independent of each other. And all that really means is that the error terms are kind of random. In other words, the points are randomly scattered around the line. Sometimes we have positive errors, sometimes we have negatives. But look at the one on the right. We have a string of positive errors followed by a string of negative errors. That's not independence. Okay, there's some, for whatever reason, when there's a positive error, there's a tendency to be another positive error. When there's a negative error, there's a tendency to be negative. So the one on the right violates the assumptions. Oh my God. And that means we have to do something about it. Just like changing our scale. Okay, we fix the scale when we find that it's always too high or too low. All right, and now the last thing I just want to mention here is that there's multiple different kinds of techniques we can use to carry out a regression analysis. The one that we're using is called ordinary least squares. All right, so let me give you a second to catch up. We're just going to briefly mention a couple more terms, and I think we'll have to stop because that way we can all be together in the classroom when we start doing actual examples on our calculators. This was a good opportunity to introduce all the assumptions in the background, but we want to be in the classroom when we're doing actual examples. All right, and that's exactly how it looks like this is going to turn out. So the name of this technique is called ordinary least squares, and it generates a sample regression line. And of course, the notation has to be a little different. So let me show it to you real fast. So what I've done here is I've written down the population regression line and the corresponding sample regression line. Okay. Let's look at the two. What's different now? Well, first of all, the Greek letters are being replaced with the Roman letters. Beta is being replaced with B, at least as far as the intercept and slope go. The Y, though, Y was already a Roman letter, so we couldn't do anything about that. So a common method we use in statistics to indicate an estimator is put this little pointy thing on top. The formal name of that symbol is the caret, but Y with the little pointy thing is called Y hat. You get it? It looks like a little hat. And that is our estimate of the population Y. So that's what our sample regression line looks like. So when we pop the data into our calculators, this is what we'll be estimating right here. The one on the top is the true population regression line. The one on the bottom is the estimated version. Now, if you notice, this one is missing the error term because that is assumed to be on average equal to 0. Okay, so there's no need to estimate it because on average it's supposed to be 0. So the sample regression line really does look like the equation of a straight line, or what we're used to seeing. All right, what else do we need to know? All right, one more piece of terminology, and then I think we'll have to stop here. The corresponding sample error term, actually, let me throw this in here. The sample version of the error term. Remember, we've written it as epsilon I. Oh no, where is it? Here it is. Yeah, that's one thing I don't like about PowerPoint. It's kind of a nuisance. Subscripts are kind of a nuisance, especially with single letters. It seems to be particularly stupid about that. See, you'd think they'd put it on this little formula bar, but they don't. That would be too easy. Yeah, it's really frustrating. It's just not getting the point. All right, I'll just leave it like that for now. Is known as a residual, and it's written as just EI. Okay, so the term notation is epsilon. It's an error term. EI is the residual. It's the population version. And this is the sample version. But in both cases, what they both represent the actual Y minus estimated I. In other words, the regression made a mistake. So the formulas that we'll be using or regression analysis are based on a model where our goal is to do the following. Let's jump ahead here. The OLS technique we'll be using was chosen to make sure that it minimizes the sum of the squared errors or residuals. Now, you don't have to, yeah, you should remember this, but we're not going to do this ourselves. That would be too complicated. So instead, we'll take the results that they give us and run them with our calculators, but this is what they're doing behind the scenes. They're making sure that all these error terms or residuals actually are as close to this line as possible. I mean, that's really all they're doing in a nutshell. All right. So I think we've had enough of this for now. We'll come back next Tuesday and we'll pick it up. We'll review this again because it's very complicated, but what we want to really do is dive into the examples. That's when it starts to get interesting. And then we'll learn all the ins and outs of analyzing our results. All right, so if there's nothing else, I guess you can go home and enjoy your, or if you're not already home, you can go and enjoy your Thanksgiving break. And I hope you have a good time. And I'll see you all next Tuesday. Oh, here's a chat. You're welcome. See you later. You're welcome. Have a nice break. Bye.